Hi there and welcome to this video for Senior Physics looking at quantum mechanics. In this video we're going to explore the idea of the photoelectric effect, first put down by Max Planck. Now Max Planck basically worked and generated a photoelectric cell, and some of the evidence that he produced was then put together by Einstein to put forward a theory that light came in the form of particles or was made of quanta. But what was the photoelectric effect itself? Well, the photoelectric cell can be seen down here in a very diagrammatic version. There's a metal plate, and you can see that metal plate with the orange in the orange color. It is placed inside an evacuated glass cylinder. Now that glass cylinder has no air in it, and that's important because we don't want to cause electrons to be generated from the air, and that will seem more reasonable when we move on through the explanation. To the right hand side of the metal plate we've got an anode, which basically just a metal pole. That's attached to wires that then runs through a micro ammeter. Now we're hopefully going to move very small electrons from one place to the next. Because they're small electrons, we're going to only get a small amount of charge that's going to move, hence we're only going to get a very small current. We've got a light, and the light can change. We can change our frequency. Now remember what Max Planck said from our previous video. Max Planck said that energy is proportional to the frequency of light. So if we change the frequency of light, we're going to increase or decrease the amount of energy. Now metals have free outer electrons on the very outside shell of their atom, as we know today. Now what Max Planck did, he changed the wavelength of the light, thus changing the frequency. By changing the frequency, it allowed him to change the amount of energy which was given to the electrons. And what he found was that at certain frequencies of light, electrons would be emitted, and as a result, a current would flow. So what basically happens is electrons will be emitted from the metal at a certain frequency or wavelength. They would move towards the anode, and as a result they would flow through past the ammeter, and a photocurrent would be set up. So let's give a very simple version as to how this experiment works. So to start off with, let's explore the idea that light only works at specific wavelengths or frequencies. Now, metals will basically emit at certain frequencies, which we call the threshold frequency. That threshold frequency is given the symbol F with a subscript O. So let's turn the light on at a very low frequency on the red scale. So if we turn the red light on, we notice that no electrons are going to be emitted. So as a result, nothing happens and nothing will be read on the ammeter. But let's put yellow light on, and immediately yellow light emits certain electrons. So those electrons are emitted, they come out, and they don't really do a lot. They have just had enough energy to break free from the hold of the nucleus and actually become free electrons. But what happens if I actually increase the frequency? So we can see here that we've got a specific amount of energy which is going to generate our electrons to be emitted. But if I increase that frequency, maybe I'll look at green light. So I'm going to increase that frequency and see what happens. Now the electrons are actually given a little bit more energy. Now because the energy is quantized, all the energy is given to the electron. So some of that energy is utilized to break free of the atom, and the rest is converted into kinetic energy. The result is I get a photocurrent. Well, let's go up one a little bit more and let's see what happens when we add blue light. Now you'll notice that the electron moved across a lot quicker. Because it moved across a lot quicker, we're going to get an increase in photocurrent. And if I put on purple light, which is the higher end of the visible white light spectrum, I've got increased frequency, and as a result I've now got a lot more kinetic energy, which means I get an increase in my photocurrent. So obviously frequency has an effect on firstly emitting the electron from the atom and then giving it kinetic energy, thus increasing the current itself. We can also have a look and see what happens if we increase the intensity. Now you can see here we've got 4 bars on all of our lights. So let's put on green light, and you can see there it's got a lot more intensity, there's a lot more rays. What is going to happen? Well, you'll notice because it's green light we get some slow movement, but look at the number of electrons. we've got a lot larger number of electrons which are moving, and as a result, because we've got more electrons, we've got more photocurrent which is going to be generated. So as a result, the intensity actually increases the number of electrons which are going to be emitted from the actual metal itself. Okay, so what were the theories that came about? Well, photocurrent is proportional to the light intensity. The brighter the light, the more electrons are going to be emitted. We also found that the electrons were ejected immediately, which is basically goes against what happens in wave particles. As soon as the light basically hits the metal, that electron is emitted straight away, whereas in wave theory it would take time to build up. Also, we know that the photocurrent depends on the frequency. I can have really bright red light, doesn't matter what the intensity of red light is, it is not going to have enough energy to allow the electron to break free of the hold of the nucleus. However, I can have a very low intensity ultraviolet ray which has got high energy, and that will be emitted straight away and cause a photocurrent. So basically, the type of frequency that is generated from the light will determine the amount of electrons which are going to be emitted. Remember that it's an all or nothing situation because the light is quantized. You've got to work on the principle that each quantized piece of light is giving its energy to a specific electron. If it's enough energy for it to allow it to jump free of the hold of the nucleus, then it will be emitted. If its energy is greater than that, then that extra energy will go into kinetic energy. So basically we notice that anything below that threshold frequency, then there will be not enough energy to jump and leave the leave the nucleus, hence it won't be ionized and it will drop back, and more about that later on. So let's look at some of the calculations we can use with this. Well, first off, we're going to look at our work function. Now, work function is basically the amount of energy that's required to emit the electron from the atom. It's the total amount of energy to allow it to break free from the hold of the nucleus. And this will happen at a specific frequency per specific element or metal. And we give that symbol, as I said earlier, F subscript 0 or O. Anything higher than FO, or the threshold frequency, will give added energy to the electron, and it will come off in the form of kinetic energy, thus increasing the photocurrent. Anything below that frequency, there will be no electrons liberated, hence we get no current. So what we're finding here is that because we're actually getting times when there are no electrons emitted and then times when there are electrons emitted, this is good evidence for the idea that the light is actually acting as a particle and in little quantized amounts. Now the work function, and it's given the Greek symbol psi, can be calculated as the energy at a specific frequency or threshold frequency. So psi basically will equal HF subscript 0. Now remember, we had earlier that E equals HF, that allows us to work out the energy of a certain frequency of light, but for the work function, this is the total amount of energy allowing the electron to leave the hold of the nucleus. So that will only happen at the threshold frequency, hence HF0. Anything greater than that, and then we get the two formulas that you can see on the right hand side. The kinetic energy, or the maximum kinetic energy, will be made up of HF. Now that will be the amount of energy for a specific amount of light greater than the threshold frequency, minus the energy which is made up to actually release the electron. So if you can imagine it like a piece of cake, what you tend to get is, if you've got a frequency or an amount of energy greater than the threshold, a portion of the cake is used for the energy necessary to break free, and the rest that's left over is given to the electron in the form of kinetic energy. So what we've done in the third equation down the bottom there, we've got EK max equals HF minus HF0. That basically takes away our threshold frequency energy from the total amount of energy, and as we said, what's left over comes off in the form of kinetic energy. So I hope you found that useful with respect to those calculations. How else can we look at work function? Well, we can look at it on the form in the form of a graph. And in this case, we've got frequency along the bottom in hertz times 10 to the 14, and we've got the kinetic energy in times 10 to the negative 19. Now you will notice where the line crosses the x-axis, so for metal 1 and metal 2, where it crosses the x-axis at 2 and 4, that is basically the threshold frequency. You'll notice at that point the kinetic energy is actually 0, so there's no movement. So we can use the graph to determine the threshold frequency for a specific type of metal. You'll also notice that the gradient is the same for both. Well, the gradient of both those lines is going to be Planck's constant. So as a result, Planck's constant, 6.63 times 10 to the negative 34, will be the gradient of that line, and hence they're both parallel to each other. We also know that if we increase the frequency beyond that of the threshold frequency, we will increase the amount of kinetic energy. And you can see that for metal 1, threshold frequency is 2 times 10 to the 14 hertz, but if I went to 4 times 10 to the 14 hertz, you'll notice I'll get 2 times 10 to the negative 19 joules of kinetic energy, which is generated. Now, if I know that, then I actually can then work out what the speed of the electron is moving at if I know its mass, and I'll just use EK equals a half mv squared and rearrange it to find V. As I stated, the gradients of metal 1 and 2 are equal, so as a result, Planck's constant obeys the laws for every single metal. But you'll notice that all the threshold frequencies for every single metal will be different. Why is that? Well, each of the metal structures, the atomic structures, are all different. They've all got different charges in their nucleus, and as a result, they've got different holds on the outer electrons. So it's easier or harder to emit those electrons. Okay, as I said, different metals require different work functions to release their electrons. Well, I hope you found that useful. I hope that sort of explained the photoelectric effect to you. Do watch my next video on this link, because I will use the PhET simulation to try and explain in further detail how this works using some actual evidence. Do check out my website, aussiephysics.com, and that will basically give you other iTunes U courses that you can go on, and also worksheets. So I hope you found this video useful. Thanks for watching, and I look forward to you joining me again. Bye for now.